Okay, so in our last two classes, we looked into the behaviors of ideal and non-ideal solutions. Under non-ideal solutions, we learned two types: those which showing positive deviation from the Raoult's law, the other showing negative deviations from the Raoult's law. There is one more category of solution showing positive deviation. Those are the ones which have very large deviation from Raoult's law. So when they have very large deviations from Raoult's law, how does their vapor pressure curve look like? Their vapor pressure curve looks like this, basically. Uh, you can see, if you can recall the vapor pressure curve of solution showing positive deviation, how was it looking? It was just deviating from the ideal behavior, in the sense there was a small bulge, small hump-like curve structure. But you look at the vapor pressure curve of this solution. In fact, one example for this solution showing large deviation from Raoult's law is ethanol water mixture. You see there is a large hump. That means vapor pressure of the solution. See, for solution showing positive deviation, what is the characteristic? Vapor pressure of the solution is at some fraction, at a particular mole fraction, at particular composition, is greater than that of pure liquids A and B. What about positive large deviation from Raoult's law? Is not just greater, is far greater, is very much greater at a particular composition of the solution. Vapor pressure is too high than compared to the vapor pressure of pure liquid A and B. Therefore, uh, therefore, such solutions do exist. This is what I was talking about. Small positive deviation from Raoult's law. Look at the curve here. Very large deviation from Raoult's law. What are the examples of this kind? Very large deviation from Raoult's law. Ethanol water mixture. Now, since we have completed the characterization of ideal and non-ideal solutions, we will now move into another aspect. That is, how does the boiling of solutions get affected by the composition of solutions? What do you mean by this? What do you mean by this? How does the boiling of solution gets affected by the composition of solution? Before that, we will see how the boiling point of a liquid and vapor pressures are related. They are related like this, is it not? Liquid. When does a liquid starts to boil? I mean, this is what you have learned in your polygative properties chapter. When does a liquid start to boil? A liquid starts to boil when its vapor pressure becomes equivalent to external pressure. Is it not? And in most of the experiments we do, that external pressure, we take it as atmospheric pressure. So when the vapor's pressure start becoming equal, or when vapor pressure becomes equal to the atmospheric pressure, the boiling starts. Now, why do different liquids have different boiling points? Because they have different vapor pressure. And you know that vapor pressure is also affected by temperature. So how to, a liquid which is not boiling at room temperature, how to make it boil? Basically, you start heating it. Go on heating it until it reaches its boiling point. But from the vapor pressure point of view, what do you mean by reaching this boiling point? As you heat the liquid, vaporization is more. Vaporization is rapid, vaporization increases, and more vapors collect over the surface of the liquid. What does this do? What do these vapors do? They increase the vapor pressure. So as you heat more and more, vapor pressure increases to higher values and keep heating. So what happens? At one point, that vapor pressure can become equal to, or will become equal to, atmospheric pressure, external pressure. At this point, the liquid will start boiling. So We can simply put a relationship like this. It's not. Increase in the vapor pressure causes decrease in boiling point. So vapor pressure and boiling points are inversely proportional, and vice versa. Decrease in the vapor pressure causes increase in the boiling point. Now, maybe we have always pondered with this question. We have played with this question. Is now, why does water boil at different temperatures in different places? What is the boiling point of water? It is 100 degrees Celsius. Where? At sea level, at mean sea level. Is it not? So, at 100 degrees Celsius, water boils at sea level. At what temperature does it boil in Bangalore, Tumkur? Example. Recording boiling point is a very common experiment. Right? You would have even done this in your high school. At what temperature does water boil in Tumkur? Example. Not at 100 degrees Celsius. At much lower than 100 degrees Celsius, maybe 97, 98 degrees Celsius. Why? Because the atmospheric pressure in Tumkur is much lower than the atmospheric pressure at the sea level. So when the atmospheric pressure is lower, you can make the vapor pressure of the water equal to lower atmospheric pressure at a lower temperature. So that's what happens. So these are the things we know about pure liquids. How the liquid starts to boil when its vapor pressure becomes equal to atmospheric pressure. So you have to heat it a bit. Okay, but this concept of vapor pressures and boiling point, we will extend it to solutions now. Now I mix two solvents, A and B. Does this solution also boil? Yes, of course. If you heat, the solution also boils. Now record the boiling point of this solution. What do you see? Depending on the type of solution, whether it is ideal, non-ideal, you see difference in the behaviors. You see a variation in the boiling point of the solutions. Now let us take up this issue of temperature against vapor pressure curves. This is also called boiling point vapor pressure curves. For an ideal solution, this temperature vapor pressure curve will look like this. So, this is also called a phase diagram of solutions, basically. This is the finalized phase diagram after following steps. Finalized phase diagram after constructing the phase diagram. Now, let us see how to arrive at this curve. Let me dissect out different components of this curve and see how this final curve has been arrived. Now, what are we talking of? We are talking of temperature vapor pressure curve of ideal solutions. Right. Okay. Let us take the simple axis first. On the y-axis, you are going to plot the boiling point. On the x-axis, you are going to plot the mole fractions of the solution or compositions of the solutions. You can either express the composition in mole fraction term or percentage by weight. Different books express as different terms, but please remember that mole fractions and percentage by weight are not equivalent. Mole fraction is the fraction of the moles. Percentage by weight is fraction by the mass. In fact, they can be interconverted using n is equal to number of moles is equal to weight by molecular weight formula. Fine. Now, where is the boiling? The liquids I have taken on this curve are A and B. Where is the boiling point of B? Much lower, is it not? On the x-axis, printed in green. Where is the boiling point of A? Much higher, printed in red. So what does it tell about the nature of A and B? The volatility is not same. B is more volatile than A. Therefore, it is boiling at lesser temperature, lower temperature than A. Now, the simple thing, is it not? Take A, record its boiling point, plot on one axis. Take B, pure B, record its boiling point, plot on one axis. In fact, the points I have shown here is for clear understanding. I have taken A and B, which much bigger difference between their boiling points. You can even take liquids of smaller difference, but understanding sake, let it be the difference shall be bigger, very much bigger. Okay. Now, this is the second curve. In the second curve, what have I done? I have not just recorded the boiling point of pure A and B. I have recorded the boiling point of solutions of A and B at different compositions and have plotted the boiling point. How is the picture of, how is the nature of the plot? Actually, when I am talking about ideal, Raoult's law, ideal solutions, that should have been linear, like how the vapor pressure varies against mole fraction. That should have been linear. but it is not linear. Practically, it is not linear. It is a bit drooping. It is bit dropping. But in any case, no point in the solution or none of the solutions of any composition, boiling point cannot be lower than that of pure B and cannot be higher than that of pure A. So, lowest boiling point is still of pure B's, highest boiling point is still of pure A's. In between are the boiling points of solutions of different compositions. Fine, no problem. Till now it is very easy and understanding is very straightforward. The next curve requires a bit more concentration from your side.
Thank you.
Yeah, sorry. The next curve requires a bit concentration from your side. Now, let the liquid of some composition boil. Okay, fine. You know the composition of the liquid, right? What is the percentage of A in that liquid in the solution? What is the percentage of B in the solution? You know the composition of the liquids in the solution. Now, for that composition of liquid, when it is boiling, please remember, when it is boiling, what is the composition of vapor? This is the question. So now we are adding an extra dimension here. What is that extra dimension? We are not just looking into the composition of liquid. We are also looking into the composition of vapor. When it is boiling. You can look into the composition of vapor at any temperature basically. But we are looking into the temperature at boiling point. So how to do this experimentally? You collect the vapors when it is boiling. Condense the vapor. Find out the liquid's percentage. Now for example, I have taken a solution of 30% B. Remaining 70% is A. Ideally, what is expected? The vapors should also have 30% B, 70% A. Is it not? But that doesn't happen. In real solutions, that doesn't happen. What happens then? Usually, the vapors are rich in more volatile liquids fraction. That means, if in the given example here, B is more volatile. So when you collect the vapors at the boiling and see the composition of A and B after condensing that vapors, you see that B would be present at a higher percentage than 30% actually. It will be more than 30%. You take any composition like this, 70%, 80%, 90%, 90%, any composition, you always find the vapors are richer in vapors of more volatile liquid. Okay, fine. Now what you have to do is, after finding out the composition of vapors, plot it again using on a new curve. That means now here I have plotted in pink color. What is that pink color dot represents? Composition of vapor of a solution of liquid composition in blue dot. Okay. Since the composition of vapor and liquid are not identical, we get two different points. Had they been identical, the points would have been same. They are not identical because I told you the vapors are richer in more volatile fraction. Fine. Now, go on doing this for a number of compositions of the liquid. You prepare solutions of varying concentration of A and B, a number of solutions of varying concentration of A and B. For each solution, boil the solution. During boiling, collect the vapor, condense the vapor, find out the composition of A and B in the after condensing. What did I tell? They will be different. They will not be equal to the liquid you used for the boiling. So go on doing for this a number of solutions. You finally will get, you finally will get a curve like this. What is that? The blue line represents composition of liquid. What does pink line represent? Composition of vapor. Actually, this is what is the curve I showed here. In this slide, I explained how to construct this diagram, phase diagram. Okay, so at once it is difficult to understand this diagram, but as you dissect it into different parts, you can understand it easily. So now for any solution, I can construct a phase diagram of vapor composition and liquid composition and their boiling points. Okay, fine. And this is for ideal solution. Now that is what I said here. So how to understand this diagram? I will just take a section of this diagram at some points, at few points. For example, I have taken the liquid of composition C1. Okay, so going by the diagram, is the C1 richer in A or B? C1 is richer in A because it is nearer to the mole fraction of A of pure liquid 1. It is nearer to that. So C1 is richer in A. No problem. But which is the more volatile liquid? B is the more volatile liquid, not A. So at C1, start heating it. The solution of composition C1 will boil at T1. That is the boiling point. T1 is the boiling point of solution of composition C1. Now collect the vapors at this temperature and condense those vapors. Find out the composition of the liquids in the vapor. As I told before, that will be richer in B because B is the more volatile component. So now you basically, once you collect this, what have you got? You have got a liquid of different composition, C2. Is it not? So you can go on doing like this for a number of sets of points. C1, C2, C1, T1, C2, C1, T1, C2, T2, C4. I go on doing like this for a number of points. So what you can do basically, if you do like this, what will happen? As you go on doing this, collect the vapor, condense it. And the new composition is richer in B. Boil that new composition, collect the vapors again, condense it again, get another composition that will be more, that will be much richer in B. You can go on doing like this. Heat, boil, vaporize, condense the vapor, get the new composition of the liquid solution. Again, reheat it, repeat the steps, repeat the sequence for a number of times. So what would happen finally? With every step, with every progressive step, you will be having new liquid composition which will be increasing its content of B. With every cycle, with every set of experiment, cycle of experiment, it will be increasing its composition of B. So in fact, you can finally reach B at one point. Is it not? Pure B at one point. So what have you done basically now? If you do all these things, what have you done basically? You have separated B out of solution A and B. Is it not? By using the technique of boiling, collecting the vapor, condensing them. Boiling, collecting the vapor, condensing them. In fact, this is the basic principle of fractional distillation. However, when the way I explained this, appears that fractional distillation will be very tedious. Is it not? For every time we should go heat, condense the vapor, reheat the solution, condense the vapor, reheat again, condense the vapor, go on doing like this until you get pure A or B. But however, although the principle is this, but the experimental part of the fractional distillation has been improved a lot. The principle has not changed. The principle is still this. Has improved a lot and has been automated nowadays. So a fractional distillation column can easily separate A and B by using boiling points difference of A and B. Okay, fine. Now that is about ideal solutions. How does this boiling point composition curve look like for non-ideal solutions? Is it not? It's like this. Non-ideal solutions. Temperature vapor pressure curve for, actually that should not have been temperature. Boiling point vapor pressure curves. Take it as boiling point vapor pressure curves. For mixtures with large positive deviation from Raoult's law. Actually, you can plot this for any type of solutions. Even you can plot this for solutions with small positive deviation from Raoult's law. But what happens? The lines will be very overlapping because the difference is small. Therefore, I have taken an example where there is large difference. That is for our better understanding sake. Anyway, the argument doesn't change. Even if I take this example, the principles and the argument logic doesn't change. Basically. So let us do a small experiment. Let us do an experiment. I have taken an ethanol water solution. Now go and look at the vapor pressure curve for ethanol. Okay, fine. What did I tell here? What did I tell here? Very important. This curve attains the maximum value of vapor pressure. For what composition of ethanol? For 0.9 mole fraction of ethanol. So remaining 0.1 is water. So if I take 0.9 mole fraction of ethanol and 0.1 mole fraction of water, that solution has the maximum vapor pressure compared to pure ethanol, pure water or solution of any composition. It will have maximum vapor pressure. Now you relate this maximum vapor pressure to its boiling point. So ethanol and water has maximum vapor pressure at 0.9 mole fraction of ethanol. Fine? Okay. I told you vapor pressure and boiling point are inversely proportional. So if I take this solution of 0.9 mole fraction ethanol and record its boiling point, that boiling point will be the minimum boiling point of all possible solutions of ethanol and water, including pure ethanol and pure water. Okay, that is a minimum boiling point. Do we have experimental values to substantiate or to justify these claims? Yes. Boiling point of pure water, as you know, it is 100 degrees Celsius. Well, because this 100 degrees Celsius is at sea level, or simply putting, is at 1 atmospheric pressure. The experiment was done in 1 atmospheric pressure, 100 degrees Celsius. Boiling point of pure ethanol, 78.5 degrees Celsius. Now, what is the boiling point of ethanol water mixture at 0.9 mole fraction of ethanol? It is 78.2 degrees Celsius. So what is the difference of pure ethanol and the minimum boiling point value? 0.3 degrees Celsius. Let us look at this in terms of boiling point vapor pressure diagram. Same thing. What we looked at the previous one for the ideal solution, the same thing, except the curve is not symmetric as it was in ideal solution. Rather, curve is having a shape in which there is a minimum value of boiling point. Okay, there is one more interesting point. At this minimum value of boiling point, that is 0.9 mole fraction of ethanol, the compositions of vapors and liquids are becoming identical. Okay, are becoming identical. Anyways, this we will take up when we talk about distillation in our future classes. This minimum, when the point where the vapor composition and the liquid composition, or the temperature at which, or the boiling point, okay, simple. The temperature at which vapor composition and liquid composition become identical, That we will talk of in our future classes. But anyways, as of now, what I want you to know is the curve is not identical to that of, or the diagram, sorry, not the curve, because it contains two curves. The diagram is not identical to that of ideal solution. It is rather distorted, is it not? It has a minimum point, which was not present in ideal solution. Basically, how was the curve looking for ideal solution? Like this. Now compare this with this. Okay, that is a vapor composition, and boiling point of pure water is shown 100 degree. Boiling point of pure ethanol is shown 78.5 degree. Now boiling point of 95.6% ethanol solution is 78.2 degree. That is also shown. So you prepare solution of any other composition apart from 95.6% of ethanol, you don't get it below 78.2 degrees Celsius. Is it not? Fine. That is how a curve of this nature looks like. Now we will take up one more example of mixture showing negative deviation from Raoult's law. So how would the mixture showing large negative deviation from Raoult's law look like? The vapor pressure curve looks like. The vapor pressure curve will have a depression basically. It will have a minimum point for a particular composition of the solution. So at that point, the vapor pressure is minimum. Now please relate this vapor pressure of the solution to the boiling point of the solution. Since the vapor pressure is minimum, the boiling point would be maximum. Example, nitric acid water mixture. The minimum vapor pressure for a solution is 68% by mass of nitric acid. So at this 68% by mass of nitric acid composition, the boiling point is maximum. Boiling point of pure water 100 degrees Celsius. Boiling point of pure nitric acid, oh I'm sorry, it is not 100 degrees Celsius, it's a typographical error. Sorry. Boiling point of pure nitric acid is, let me see at this curve, it is 86 degrees Celsius. 86 degrees Celsius. Boiling point of pure nitric acid is 86 degrees Celsius. I'm sorry for this typographical error. I'm extremely sorry. Anyways, now what is the maximum boiling point attained by a solution of any composition? It is 120.5 degrees Celsius. At what composition? At 68% by mass of nitric acid, you get boiling point 120.5 degrees Celsius. So look at the curve. The curve is having a maxima in it, unlike in the ethanol water mixture which was having a minimum boiling point. This has a maximum boiling point. Again, at that maximum boiling point temperature, at 68% by mass of nitric acid, the composition of vapor and the composition of liquid are becoming equal, are becoming identical. What is the significance of that point I am talking about, where the composition of vapor and composition of liquid are becoming identical? The significance of that point we will talk about when we discuss distillation processes and the principles involved in distillation. Anyways, so now as of now, like I told you, you have to use this curves for distillation processes. Let me now give you a hint of how to use this curve for distillation processes. Now, example, I am going to, first of all, what is a nitric acid? What is dilute nitric acid? Dilute nitric acid is nothing but nitric acid solution made in water. So dilute nitric acid is nothing but an example for solution showing large negative deviation from Raoult's law. Okay, so to do this experiment, we need not have to find a very expensive chemical. Simply a dilute nitric acid solution you can use for your experiments of vapor pressures and boiling points, negative deviation from Raoult's law. Okay, fine. Now let us consider a solution of composition C1. Okay, where is that C1? that is nearer to 100% water. That means the content of nitric acid is less. It's a very dilute solution of nitric acid. Okay. Anyways, what is the composition? What is the boiling point of nitric acid? 86 degrees Celsius. What is the boiling point of water? 100 degrees Celsius. So basically, what have we learnt in our lower classes about distillation? You start heating the solution. The liquid with lesser boiling point will distill first, will vaporize first. That is what we have learned, is it not? But actually, it doesn't work in that way. See what happens. The fractions, the vapors which are coming out when you are going to boil dilute nitric acid is that of actually water, is that of water. So you go on doing this, you start distilling dilute nitric acid. Although nitric acid boiling point is 86 degrees Celsius, it doesn't come out. Water comes out instead. Water comes out and you can collect pure water if you distill dilute nitric acid. Therefore, the understanding of this boiling point vapor pressure curve is necessary to understand and to carry out distillation processes to separate liquid successfully. Fine. So that is what vapor pressure and boiling point composition curves teaches us. I mean, is a guide to us. So, anyways, so I will stop my lecture here. Next class, we are going to see how the next class we are going to see distillation process.